I'm Louis Wagaspak, Thermal Analysis Product Manager at TA Instruments. I'd like to welcome you and thank you for joining us for today's webinar. During the webinar, you can customize your viewing interface by arranging windows to your liking. You can resize the video and slide windows independently from one another by clicking and dragging the bottom right corner of each window. If you get disconnected at any time, please use the instructions you received to log back in. You can access several different content windows by clicking the widgets at the bottom of the screen. These include speaker bios, additional file downloads, and social media interactions. If you need help, click the question mark widget. Please ask any questions you may have at any time during the presentation by submitting them through the Q&A window. We will answer as many of these as possible at the end of the webinar. Our guest speaker today is Roger Blaine. Dr. Blaine holds a PhD in analytical chemistry from Oregon State University. Roger has over 100 publications on the applications of thermal analysis. He is a founding member of the ASTM International Committee on Thermal Analysis and the Thermal Analysis Forum of the Delaware Valley. Roger is an emeritus member of the North American Thermal Analysis Society, having served as its president, vice president, secretary, and treasurer. Roger retired from TA Instruments after 40 years as a principal scientist. He currently serves as a consultant for thermal analysis standards and regulatory affairs. The title of Roger's presentation today is Practical Aspects of the Kinetic Determination by Thermal Analysis. Roger?
Thank you, Louis, and welcome to everyone. Today we're going to be talking about some of the practical aspects of the determination of kinetic parameters by thermal analysis, and in particular, thermal gravimetry and differential scanning calorimetry. To begin with, we need to define what is kinetics. Kinetics is the study of the reaction rate of a chemical reaction, the rate of reaction with time and temperature. My favorite example of this is the cooking of a soft-boiled egg. I like 3-minute eggs, and when I bring the water to a boil on the stove, a nice, vigorous rolling boil, when I put my egg in and take it out 3 minutes later, it's just done to the correct doneness. But every once in a while I get impatient, and the water is not yet to a full rolling boil at 100 degrees Celsius. It's at that point where the water is boiling on the bottom of the pot, but the bubbles are not reaching to the surface. That is, the temperature of the water is not yet at its full 100 degrees C. If I put in my egg at this stage of the game and then take it out 3 minutes later, it will be underdone. I need to let it remain in the water for perhaps another minute or so. This is the concept of the relationship between time and temperature for a chemical reaction, and in this case, the chemical reaction is the denaturation of the protein of the egg. Now, kinetics are described by what is called the general rate equation. This is a combination of two equations, the Arrhenius equation generated in the 1890s, and the law of mass action generated by Goldberg and Vaga in the 1860s. These two are combined in this particular form. On the left-hand side of the equation is the rate of reaction. On the right-hand side, there is the term Z, which is called the pre-exponential factor. It's the rate of reaction at infinite temperature. The next term is described as F of alpha. That is, it's the kinetic expression, the model for the particular reaction, how the reaction depends upon the concentration of the reactants. And finally, on the right-hand side, we have an exponential term in which we have the activation energy, one of the parameters that we want to determine, and reciprocal temperature. Now, the conversion function, this function f of alpha, has a variety of forms. The most commonly encountered form is called nth order reaction, in which the reaction is just proportional to the amount of the reactants left to react. There is another form called the autocatalytic or accelerating reaction, sometimes called the Shestak-Berggren equation, in which there is another term added, in this case the amount to react raised to another power, in this case m. What happens here is that as the reaction proceeds, the reactants themselves catalyze the reaction, and it proceeds more rapidly. These two reaction models are the ones that most commonly encountered in thermal analysis, but they are not the only ones available. The dots down the page indicate that there are other models that we might use. Now, the goal of kinetic studies is to determine 3 or perhaps 4 kinetic parameters. The first of these is activation energy. That's the term capital E. The second term is the pre-exponential factor, often expressed as its logarithm. And as I mentioned a moment ago, this is the reaction rate at infinite temperature. And finally, there are the two terms, lowercase m as in Mary and lowercase n as in Nancy, which are called reaction orders. There are a series of commonly used differential scanning calorimetry methods. They fall into a series of 3 classes. The first of these are single heating rate methods, and the method of Borchardt and Daniels from the University of Wisconsin is an example of this. This procedure can be found in ASTM standard E2040. The second class of materials are called the variable heating rate methods. These include the Ozawa-Flynn wall method, as manifested by ASTM standard E698, and the Kissinger method, as manifested by ASTM standard E2890. And finally, there is a group of isothermal methods which can be used for autocatalytic or nth order reactions and can be found in ASTM standard E2070. Now, I give you these references to the ASTM standards because if one goes back to the original articles by the respective authors, they often are cumbersome with regard to mathematical derivations and demonstration of applications. The ASTM standards give us a specific way and set of instructions that help us make the determination, and they are probably the first place that you as the user ought to go for your information. Now, to begin with, we start with the Borchardt and Daniels method. This is among the easiest methods to use. We just run a single DSC exothermic trace. We measure 3 parameters, well, really a series of 3 parameters. You can see that the exotherm has a vertical bar, in this example, about 490 Kelvin. The vertical bar divides the area of the exotherm into parts. The total area represents the heat of reaction. The amount of the reaction from the vertical bar to the right represents the amount of reaction left to proceed and is our value for A. The vertical line, which is the rate of heat flow, is the rate of the chemical reaction. So we have all of the parameters that we need for the determination of kinetics. We have the temperature, we have a rate of reaction, and we have the amount of a reactant left to react. We can use the equation as generated by Borchardt and Daniels to make this determination. On the left-hand side is the logarithm of the rate of the reaction. On the right-hand side is the activation energy and reciprocal temperature. And so if we plot those two functions, the intercept of this equation for a straight line gives us the log of the pre-exponential factor. And from that, we can subtract the conversion functions to obtain the pre-exponential factor from the intercept values. Now, these equations look really complex and cumbersome. They can be, but of course, software available from TA instruments will make these determinations for you very easily, but they're not all that difficult to perform by hand as well. The second kind of reaction is the variable heating rate method. This is one in which we take a series of test specimens, 4 or more. We heat them at a series of heating rates, shown here between 1 and 20 degrees C per minute. And as the temperature, the heating rate increases, the reaction rate moves to a higher temperature. Now you notice that in this case, since this is a decomposition reaction, the reaction is endothermic rather than exothermic. These kinetic processes can be used for both endothermic and exothermic reactions. Now, the Flynn and Wall, or the Izawa Flynn and Wall method, is an example of a variable heating rate method. On the left-hand side of the equation is the logarithm of the heating rate, and on the right-hand side we have the logarithm of the temperature for the point of constant conversion. In that curve we showed you just a moment ago, it's the peak temperature that we use as the point of constant conversion. The slope of this line is proportional to activation energy and two other terms, B, which is the derivative of the Doyle approximation, and R, which is the gas constant. These two parameters are values that we can take from the literature or we can determine in an iterative process. Another method that uses the variable heating rate method approach is Kissinger equation. And here you see on the left-hand side we have the heating rate divided by that temperature of constant conversion, and on the right-hand side we have activation energy and the temperature of constant conversion. In this particular case, our slope is activation energy divided by the gas constant, and our intercept includes the activation energy and the pre-exponential factor. The equation is of the form of y equals mx plus b, a straight line. Turning to thermal gravimetry, there are a same series of analytical methods that are available. There is the single heating rate method. Commonly, there are two authors here, Freeman and Carroll, that's one reaction, and the Coates and Redford reaction. These reactions are available and used, but not so commonly. The variable heating rate method, here again, the Flynn and Wall Ozawa method, as manifest by ASTM standard E1641, or the Kissinger method, manifest by ASTM standard E2890, are the two that are most commonly used. There are, of course, isothermal methods and a new approach to kinetic parameters, modulated thermogravimetric methods. This includes the factor jump method of Joe Flynn and Brian Dickens, and includes modulated thermogravimetric analysis as well. This is in the process of becoming an ASTM standard, and it's hoped that this standard will be available before the end of 2014. Now, in thermogravimetric analysis work, we look at mass loss. And we have the same profile here for the variable heating rate methods that we saw in the differential scanning calorimetry. That is, the reaction rate moves to a higher temperature as a function of heating rate. The curve on the right-hand side here reflects this decomposition at 10 degrees C per minute, while the one on the left corresponds to 1 degree C per minute. As was the case in DSC, we select a point of constant conversion. In kinetics by TGA, this is usually about 5% mass loss. This is because many of the materials in which we're interested are polymers. And polymers have the ability to soak up moisture from the air. Nylon, for example, can capture about 3 to 3.5% moisture from just atmospheric air. And so when we are looking at the decomposition of the polymeric portion of a material, we want that to be the polymer that we're looking at and not just the volatilization of moisture. Shown in this particular profile on the y-axis is the heating rate determined, and on the x-axis the reciprocal temperature of that point of constant conversion. You can see that on the right-hand side we have a line for low conversion levels of about 0.5%, and on the left-hand side we have a conversion corresponding to 20% with values of intermediate conversion levels in between. The 3 or 4 traces on the left-hand side of the figure all have parallel slopes. This indicates that they have a common kind of reaction kinetics, while those 1 or 2 on the right-hand side have a different slope, and this is an indication that they behave differently. This profile or this kind of presentation is one more tool that helps us show that the 5% mass loss is a good point for constant conversion for these approaches. Modulated temperature concepts were introduced in the 1990s with modulated DSC, later modulated thermogravimetry, and finally, even later than that, modulated thermomechanical analysis. In these approaches, there's an underlying heating rate that is either constant or elevates as time progresses. Associated with these, and superimposed on these, is an oscillatory temperature program. This oscillatory temperature program permits us to treat the data in additional ways. Shown here, for example, is the decomposition pathway for polytetrafluoroethylene. You can see in red the decomposition mass loss that we anticipate, but shown in blue is the derivative of the mass loss on an instantaneous basis, and you see that the oscillatory temperature program has produced an oscillatory signal in the derivative profile. It's this oscillatory profile that helps us to obtain kinetic information. The equation for gathering kinetic profiles from modulated thermogravimetry is shown here. We won't go through the derivation of the respective components, but the terms that we need to gather include the underlying temperature, the half amplitude of the temperature oscillation, that would be A, L, which is the logarithm of the reaction rate, that would correspond to the peak and the valley of those that oscillatory derivative signal. Now, in modulated thermogravimetry, we use a Fourier transform process to be able to gather information over the complete process of the temperature program. Pardon me. If we use a sinusoidal temperature oscillation, the derivative of the oscillation is also a smooth continuous function, and this permits the Fourier transform. One could also perform the test, as Brian Dickens and Joe Flynn did in the factor jump method using stair-step profiles. Given that thermal curve that we looked at just a moment ago, here is the activation energy generated for that polytetrafluoroethylene. You see that in regions where there is no mass loss, there's no activation energy generated. The signal goes either to infinity or to zero, depending upon our software. But in between, where there's an actual mass loss region, the activation energy is calculated and remains relatively constant over the whole decomposition pathway. Now let's talk for just a moment about advantages and disadvantages of the respective methods. The single heating rate methods have the advantage of a simple calibration procedure We need to look at only a single sample. The determination is a single but rapid experiment, and it determines all three of our kinetic parameters: activation energy, law of the pre-exponential factor, and our reaction order n. This list of advantages is really powerful, but it's seldom outweighed by the disadvantages. The first of these is that this approach is only applicable to what are called well-behaved reactions. This means that the thermal curve needs to be textbook quality, smooth, continuous, without any bumps or diddles. That's a technical term, by the way. But this turns out to be not the case that we typically run into in real life. Almost all of the cases that we want to look at have shoulders or breaks in the curve, and it makes the single heating rate methods less than desirable. Now, the fact that we can run a single experiment is also a disadvantage in that kinetic determinations are often fraught with experimental uncertainty, and we gain a certain advantage by having replicate determinations. The method is thought to have poor reliability, and it's only applicable to nth order reactions, not to autocatalytic reactions. And finally, in thermal gravimetry, there is, we're taking a derivative signal to make our determination, and depending upon the filtering in your thermal gravimetric analyzer, this may not be the most accurate process. The variable heating rate methods have the application of being applicable to, have the advantage rather of being applicable to complex multi-staged reaction, and this is their major advantage. Even if you have a curve with bumps and diddles and breaks in the curve, each of those portions of the reactions can be examined by the variable heating rate methods. The variable heating rate method provides activation energy directly, and if we assume a reaction order, typically first order, then we can determine the pre-exponential factor Z. The methods are thought to have really good reliability, and they're easily performed manually if you don't have computer data analysis. Their disadvantages are that the calibration process is lengthy. Specifically, you have to temperature calibrate at each of the heating rates, and so that's a minimum of 4 calibration procedures, and if you use some additional heating rates, it could be even more. This requires a considerable number of experiments. The minimum is 4. I tend to prefer to do double that amount and perhaps even up to 10 experiments. And finally, the reaction assumes first order. For many decomposition reactions, this is quite acceptable, but it may not be for some other reactions. Now, this issue of the number of experiments that one needs to run produces the disadvantage of it takes a while to perform this test. Typically, to gather all the experimental data is about 2 days worth of experimental time, because some of the experiments have to go at very low heating rates, about 1 degree C per minute. Those take, and we're covering hundreds of degrees, so it takes some time for those curves to be generated. Finally, there's isothermal methods. These have the advantages of being able to apply several different mathematical models to the treatment of data. They can be used to determine kinetic parameters not only on nth order reactions, but also on autocatalytic reactions. So they provide the 4 terms that we're interested in: activation energy, log pre-exponential factor, the reaction orders M and N. And isothermal methods are thought to be the most reliable of the kinetic processes. There are some disadvantages here. First of these is that the reactions never go to completion. So there is some imprecision in the total amount of the reaction time. Since they're performed isothermally, the reaction approaches completion asymptotically. The experiments are very long. Isothermal experiments will typically take about a day to perform for each one. We need at least 4, so we're looking at experimental times approaching a week or so. Modulated temperature methods, however, have cut through some of these disadvantages. First of all, calibration is simple. We're depending upon a single rapid experiment. The determination of activation energy is model-free, but we can assume a first-order reaction to get log of the pre-exponential factor. One of the big advantages is since we're determining the kinetic parameters continuously, we can select the point of our reaction curve where the reaction is stable, and thereby we can have trust in our point of constant conversion. And the modulated thermogravimetry approaches are thought to be the most precise of the non-isothermal methods. Now there are those 2 disadvantages that we already talked about. The first of these is a single reaction. We probably will want to run replicate determinations, but since the reactions are fast, typically on the order of about half an hour, a couple of hours of experimental time will give us 4 or 5 replicates. And we often assume first-order reactions in this process. Now, where can kinetics be used? Nth-order kinetic reactions are mainly applicable to simple, single reactions like decompositions. These are reactions where the reaction is only based upon a single molecule, like decomposition. In decomposition, a big molecule is broken up into small parts. It can also be applicable to reactions where one of the products is in great excess. So decomposition and drying reactions are the ones most commonly encountered for nth-order reactions. Autocatalytic reactions are more interesting but more difficult to do. Thermoset cures, crystallization, induction time reactions, either oxidation induction or reaction induction time, constant temperature stability reactions are all autocatalytic in nature, where we're either dealing with a more complex reaction or a high energy reaction. Pardon me. TGA kinetics have all of these examples, but they have the one big advantage of being applicable to lifetime testing. The first step in the practical part of determining kinetic parameters is the determination of whether we have an nth order or an autocatalytic reaction. The process for doing this has 2 parts and begins with a temperature program through the reaction exotherm or endotherm. You see one such example here in which we have heat flow displayed on the y-axis and temperature on the x-axis, your typical DSC thermal curve. We integrate the peak area and we determine the overall area, and then we subdivide that fractional area into the first 10%. What we're looking for is the temperature that corresponds to the 8, 9, 10% of the overall reaction. When we have that temperature, we then conduct our second part of this process, which is an isothermal experiment. That is, we heat our DSC to this selected temperature, we maintain the DSC at an isothermal temperature, and then we submit to the DSC a sample pan with a few milligrams of the reactant. If the reaction starts at a high value, that is, it reaches its maximum rate very quickly and then decays away with time, we can be assured that we have an nth order reaction. If, however, the reaction starts low, builds to a peak, and then decays away, the reaction is autocatalytic. That is, the front side and the back side of the reaction peak have roughly the same shape. So this helps us to determine whether we have autocatalytic reaction or an nth order reaction. The second step in our process is to ask ourselves, what is the value that we intend to use for this data? That is, what is its purpose? There are two generally recognized areas. One is which we're simply comparing two materials for which one reacts faster. If all we want to know is which one reacts faster, or we're trying to conduct some kind of quality assessment of different lots of materials, then we can get by with a less reliable kinetic method. But most of our use of kinetics is for the purpose of predicting the future. And when we are working on predicting a reaction, we want to have the most reliable data available. This means we must use the most reliable methods available. And finally, we want to give a nod to the ease of use of gathering the data. The shortness of time, the ease of doing the calculations, all bear on which method we might choose. Now, the folks at TA Instruments have developed a flowchart to help us assess which of the reaction processes, which software package, which ASTM standard we might use. I urge you to, as you begin this work, to turn to your technical support group at TA Instruments or to your salesman at TA Instruments, and they'll be glad to give you a copy of this flowchart in one of the TA Instruments publications. Now, the third step, after we identify what our purpose is and what kind of reaction we're testing, is to actually run the experimental work. And fortunately for us, we can turn to the respective ASTM standards for the details of how to perform those tests. Typically, they involve cryogenically milling our test specimen to small size, so we have large surface area to volume ratio. We perform the experiments on 10 milligrams of test specimen, and then the various heating rates and other experimental conditions as described in these standards. So they're presently in existent 4 ASTM standards based on DSC. There is one present standard for thermogravimetric data with a fresh one on modulated thermal gravimetry in preparation, and it should issue before the end of 2014. Now, the last step in our evaluation of kinetic parameters is to ask the question, are the results reasonable? The reasonableness, we have a series of criterion that help us determine reasonableness. The first of these is to determine the actual imprecision in the determined data. The ASTM standards, each of which will have a specific method for determining imprecision. This is important to go through this process and to the extra work, the extra calculations, and determine these parameters. Secondly, our estimation of the nth order reaction is constrained by the fact that this should be a small integer or a simple fraction. Thirdly, the values for the reaction orders m and n should be less than 2. If someone comes to you and says, I've determined reaction order and I have a reaction order of 5, you know right away that the data is imprecise. The value for activation energy should be between about 50 and 300 kilojoules per mole. Biological reactions, low energy reactions, typically have 50 kilojoules per mole. These include things like the flashing of firefly tails or the chirping of crickets. The high values, 300 kilojoules per mole, will be for those high energy reactions such as pyrotechnics. The logarithm of the pre-exponential factor expressed in reciprocal seconds will range between about 8 and 30. And finally, we need to be aware of the interdependence, the lack of independence between activation energy and pre-exponential factor. These two terms can easily vary slightly as we go through the determination process and their application. We should not be troubled too much by this because one will compensate for the other. Finally, what level of precision should we anticipate? A value of plus or minus 10% is common for activation energy, pre-exponential factor, and reaction order. If we are able to determine values with precision greater than this, it's to our advantage. In summary then, kinetic parameters, kinetic processes are a useful tool for characterization of performance and for estimation of future performance. Thermal analysis tools of differential scanning calorimetry and thermogravimetric analysis provide a useful series of tools for examining kinetic parameters. And finally, we have available to us a wide variety of ASTM standards that provide the specific instructions on how to carry out these experiments, calculate the results, and determine their imprecision. I want to thank you very much for your attention to our discussion here today.
Thank you, Roger, for that informative presentation.